good news is that there are really no new concepts in this talk, right? AGS acceleration and booster extraction all required talking about synchro for the first time and then transition and the bunch merge and all these new things. But AGS extraction actually looks very much like booster extraction, and in some cases actually easier. Synchro, for instance, doesn't have to happen with a ramping main magnet, so things are actually somewhat simpler. So a lot of this is geography and nomenclature. But the scheme is the same, right? It's a closed bump, kicker, septum scheme, and then a transfer line down to ring. So we'll just talk, it's largely a geography lesson with some differences to booster extraction. So as I said, we'll talk about some of the tools for diagnosis and for viewing the process of extraction, some of the instrumentation that you have available when things go wrong, and a general overview of the process and the elements involved. And there's another practical associated with AGS extraction. Like I said, this is the last thing that we do in the injectors, and then it's very similar to booster extraction in a lot of ways. Again, you can think of this on two broad time scales, milliseconds and microseconds. So there's a synchro process that takes many milliseconds. That's sort of the first thing that happens. There's an extraction bump that comes up actually very slowly. It's not pulse. The extraction bumps in the AGS are what we call DC, right? Which I always find a little bit funny, right? Because they're not on the whole cycle DC, but they come up to one solid value. There's no function that you can put in and then ramp down. That takes many milliseconds. The septum is on for a handful of milliseconds, 4, I think, or 2, and then there's a kicker that comes on very fast. And I'll show you scope pictures that illustrate all that. But it's good to have in your mind that just like in booster extraction, these are separated rather strongly by time scale. And so when you have a problem, you should think about what time scale you might be having a problem. So like I said, the first thing that we have to do is get the beam near to the inside edge of the extraction septum. So the extraction area are the G and H superperiods, right? So the bump spans the G superperiod and the H superperiod. They're centered on G10 and H10. G10 is the location of the kicker. H10 is the location of the septum. So the bumps, the nomenclature of the bumps is a little bit funny, right? It's good to just clear this up, right? They're centered on, they're meant to center the beam, to bump the beam towards the outside of the ring at G10 and H10. The peaks are actually closer to G9 and H9, so G9 and H11. So they're off by 1, and very often there are some legacy things that call them G9C and H11C. So way back when, these are 3 bumps, and they used to be powered with 3 separate supplies, so that you could, just like at booster extraction or with a normal local 3 bump, you could control each component of the bump individually. They're wired now completely in series, and the polarities and the number of windings are such that you get a bump. It's not completely closed, but it will bump you to the outside. So there's only 1 amplitude involved. So it's still a 3 bump, but there's only 1 current to be controlled. Does that make sense? So it's just wired around the 3 sets of magnets in such a way that you get the kick that you like. So the residual is somewhat larger than it used to be, right? With 3, you can tune it out such that you just get a purely local bump. With the 1, there's some leakage, and I'll show an example of that. But it's also where the C comes from. There used to be an A, a B, and a C, and now there's only a C. So in some cases, I think on the PET page, we've eradicated the controls for A and B to eliminate some confusion, but the C remains. Just have that in your head. So like I said, there are two controls, one for each bump. They're an AGS extraction ring. You have this is hard to see, but you have state control and amplitude. State control triggers and amplitude control. So there are 2 triggers. There's a start and a stop, and you get and the functions are trapezoids. And the start trigger is here. So this is start. There we go. And this. Do you think I would learn? Anyway, the start trigger is the stop trigger is here. You got to sneak in from the outside. So you don't have any control over the shape of the function except for the level and the distance between these two triggers. And generally, we try to move the start as close as possible to the end of the acceleration ramp as possible. Because for one thing, just for speed, we would like the cycle to be as short as possible. And for polarized protons, right, this is the main magnet cycle. We like them to come on as soon as possible. So this is the bump, right, and this is the AGS main magnet. We'd like them to come on as soon as possible because we're going to want to take polarization measurements for as long as possible, right, along this time scale. Because the longer we can accumulate events per cycle, the fewer cycles it takes to do a polarization measurement. So we'd like the extraction step to come on and go away as soon as possible, so that we have as long as possible to take polarization. They can't come on too early because remember these are backlight windings around main magnet. So as the main magnet is ramping, there's a back EMF induced on these power supplies. And so if you try to ramp them too early, the power supplies will actually trip because they can't handle it. So we sort of cheat as close as possible while trying to maintain some stability for the power supply. These are the triggers. And usually we extract at the peak. And I'll explain the triggering for extraction in a little bit. Okay, so this is a picture of the G10 kicker. I have another picture that's important to note of what the inside of it looks like. So this says that it's triggered by FEV request. So that's actually a mistake. So it's important to realize that the triggering for extraction is a little bit funny. So FEV request is this master event, right? We talked about some processes like NSRL extraction that have no start events from which everything is delayed, right? But whereas booster extraction, for instance, has extraction start Gauss time. So there is this FEV request real-time event, right? We talked about why it can be a real-time event because we're not, the energy is fixed during extraction for the AGS, right? So we can have a real-time. FEV request happens all the time. If the event is enabled, it happens on every single cycle, whether you ask for a bunch or not. So every cycle that we sit and dump into J10, FEV request comes out. Whether that gets turned into a bunch is a matter of whether you requested it. So FEV request happens all the time in normal operation if everything is working properly. When you request a bunch with injection, for instance, what actually happens is that gets put through electronics, gets turned into an FEV bunch, right, of one or another color. And I'll talk about this a little bit later. But it's important to note that FEV request happens all the time. An FEV bunch is the event that actually gets turned into an extraction. That's what fires the kicker in the septum. Important to note also is that the extraction bumps fire on every cycle also. I shouldn't say fire because they're not called power, but they ramp up on every cycle. They're not dependent they're dependent on neither FEV request nor FEV bunch. The H10 septum is the last element that you go through, right? This is analogous to the F6 for booster extraction. So the beam is moving close to the edge of the septum, and then when FEV bunch comes along, a trigger is generated for the G10 kicker, and then we move across the septum into the field region and down the ATR. Again, so this shows the time scales pretty nicely. So this is 0.2 milliseconds per division. So this is about 2 milliseconds at the base. This is the H10 septum current. This is 2 milliseconds at the base, maybe 1 millisecond rise time. Right. This is the G10 kicker, which you can almost barely see, and on these scopes you will often miss. Very, very narrow peak there. And the DC bumps, as I said, so that's an exchangeable term. This is one of the things people refer to the DC bumps, the extraction bumps. You can't even see the ramp on this time scale. The ramp is way off on either side. In part because they have to stay on long enough before extraction, right? We don't bring them on, take them off, and then put them on again when we extract 4 bunches from the cycle. So they do stay on a long time. So these are really the 3 time scales that you're dealing with. This stays on for tens of milliseconds and is flat that whole time. So this is the picture of the inside of the D10 kicker. So in the AGS we have 2 bumps, right? We have 2 extraction bumps, but in the booster we only have 1, right? We have 1 bump for the F6 septum. So why would we need a bump for the G10 kicker in the AGS? Why bother? If we didn't need it in the booster, for instance, right? Why don't we have to be to the outside of the booster kicker? I'm surprised. This is sort of but the F3 kicker is a full aperture kicker. It is wrapped around the whole beam pipe. You cannot miss the F3 kicker, right? Regardless of where you are in the F3, you get kicked. Whether you get out is a whole different story. The G10 kicker, on the other hand, has this tiny little mouth way to the outside of the beam pipe. So this is the AGS beam pipe here, and this is the aperture of the G10 kicker. So without the G10, without the G9 bump, right, the field falls off rapidly outside here. The crosshatch area in here is meant to be the flat field region, and it falls off rather rapidly as you leave that. So the G9 bump isn't tuned properly. If it's too low or off or something like that, the beam doesn't even see the G10 kicker, right? It will stay in there. If you were looking at a pickup at that time, you might see oscillations, depending on how close you are. But you can, in fact, be firing the G10 kicker and missing it spatially because you're not anywhere near the field region. So that's important. In fact, there's a certain failure mode as you get here, right? The field lines here are meant to be straight. The field lines here are wonky, right? Nobody really, you're out of tolerance for the G10 kicker out here. So if the beam is actually here, the kick you get is thoroughly unpredictable. And so one of the things you get is this shot-to-shot jitter down the ATR. Vertical in particular, right? Because as the field lines get more, as the field lines curve more and more, there's more and more of a vertical component. So there's this sort of recognizable failure mode where on every shot you can get these wild deviations down the ATR. And typically if you tune around in the G10 kicker, that's helpful. Assuming everything is pulsing properly, right? You could also have a problem where the amplitudes of some of the pulse power are not doing what you think they're doing. But I think this is important to realize that this is a relatively small aperture way to the outside, which also poses a problem for low energy because this is meant to accept beam at our nominal AGS extraction energy, not being, a factor of 5 down from that, which is necessarily larger. This is, yep.
Is there any special reason we design G10 that way?
Why isn't it full aperture?
Yeah.
I don't know, except to say that to get a field strong enough to kick out beam of that energy, I would imagine you need a smaller aperture, right? So I mean, it would be more expensive to wrap a magnet around this whole thing, right? If the pole tips are here rather than here, you need a much stronger magnet to get the same field to kick the beam out, right? Plus which, that would mean that you would want to kick from somewhere other than the outside, right? You would want to extract from the center, which is unnecessary, right? So you don't even need a magnet that strong. Right, I can show you. Right, so if this is the AGS extraction bump, here's G10, here's H10, right? If you had a full aperture kicker that was strong enough and you decided to spend the money, you could extract from here, I suppose, right, if the geometry allowed, but why? Right? It just seems unnecessary. It seems more economical to build a smaller kicker where you're actually going to need it rather than cover the whole space.
So that is to say, for booster extraction, the energy is much lower, so
right.
It's easier or cheaper to build a full.
So the magnet isn't nearly as strong, right? The F3 doesn't have to be nearly as strong as the G10.
Okay.
There may be other reasons, but. Okay. So this is a picture of the H10 septum, right? It's coming this way. This is the outside of the ring. So this is the beam pipe at H10, right? It's all encased in this box. And again, so this is the septum, right? The current goes through here. Let's figure out which way. And this is the channel down the pipe into the ATR. So these are currents, and this is the return, right? And this is the channel. So this is just an inset of this. So this is circulating beam, and this is extractive beam. And the G10 kicker, the bumps are meant to get you near the edge of the kicker, near the edge of the septum, excuse me. And then the kicker in one turn gets you across. Okay? Very similar to booster extraction. So like I said, this is an old techno. I can make a better picture. You can see here that the claim is that outside the bump region, the residual is 0, which is not actually true. Right? This would be true if you had three knobs to tune, but we don't. So there are backleg windings around each of these completely illegible main magnets, such that you get a kick similar to this. Interestingly enough, the G10 kicker doesn't actually kick out. It kicks inside because of the phase event between G10 and H10. So to kick out, right, you'd be fighting all of this. This is the restoring from the bump and the quadrupoles. The quadrupoles and the quadrupole moment of the main magnet. So the G10 kicker actually kicks this way And so you overshoot and then come way out at the H10 septum, right? The scale here is not right. This is centimeters, and this is in a goofy unit straight section number. But the point is that the G10 changer actually kicks what you would think of as the wrong way, and then you bounce off the focusing of the AGS and then out over the edge of the septum.
I'm sorry, you say that's centimeters? Yeah, like it says it's centimeters.
Yeah, yeah. The extraction bump is that we run with now is actually smaller. It's typically about 40 millimeters. So the amplitudes we're running with now are typically more like 40 millimeters. But yeah, it's
A
a
monster,
beast.
sort of.
Yeah. So I actually think this might be the same picture from yesterday. So this is 40 millimeters right here. That line is 40 millimeters. You can see there's plenty of residual. But it has the same general shape, right? Here's the beginning of the bump, we go down. So this is G, this line is G, and this line here is H. The beginning of G and the beginning of H. So this is the middle of G. The middle of H, right, there are 20 main magnets, so 10 is in the middle. And you can see here's the bump, right? And like I said, the AGS has reasonably good pickup coverage, so you can see the structure quite nicely. And right, if this is much lower than 40 millimeters, for instance, you miss it. You miss the G10 entirely. Like AGS extraction efficiency will get unstable, and then it will just not happen. Right, beam will go past the extraction time and get dumped at J10 at the end of the cycle, as if you did nothing. And so this is a reasonable diagnostic to see what's going on. Right, the two important quantities here would be whether the bump is doing what you asked it to, and whether the average pickup, what we call a radius, right, whether the average of these guys is what you expect it to be. Keeping in mind that the average, we call the radius, we typically are talking about the average of all the pickups, right, which is going to be grossly distorted by the bump, right, you have these outliers. So it's important to know whether you're quoting the average with or without the bump, right, when you're trying to get back to some nominal condition. The control for extraction, most of it is an AGS extraction ring. So this is the synchro trigger. We'll talk about synchro a little bit in a minute. Like I said, it's even easier than Schoefer synchro, Schoefer AGS synchro, because largely because the field is flat. So we have control over the G10 kicker and then the H10 section down here. FEB request, right, is an ADO. It's worth noting that you need as many FEB requests as you have extractions. So if you want to extract 4 bunches per cycle, you need 4 FEB requests, which you can set here. So this must be protons, right, because we're extracting, first of all, way early relative to gold. Okay, now and there's only 1, right? So the extraction time for protons is about 850 milliseconds. Anybody know what the extraction time for gold is? 1800. 2300 is the first extraction, and then we extract every 100 milliseconds after that. For a brief period, it was 150 because of the new RF, the low-level RF. Rick was happier that way, but we should be able to go back to 100. I think we did. There's also a page which is really nice, AGS extraction tuning. So here is how we set how many bunches we want to take from the AGS, right? This is how 111 bunches get taken, right? So up here you see that there's a ring selector. So there are 3 options here: blue, yellow, and green. Green refers to shots you want to take to the W dump, and this largely selects what synchro you're on, and I'll explain that in a minute. This is the number of requests you want to take. So if you wanted to take, for instance, previously we were at the mercy of default bunches for green, right? You would have to take 1 or 4 on every cycle. We just take as many as you want. It would take as many FEB requests as there were per cycle on every cycle. But we can request a certain number of bunches, we say do it, and it happens. The bunch counter just counts the number of bunches, usually since the last of each color, green, blue, and yellow, since the last cogging reset for blue and yellow. So right, it's worth talking about the G10 fine delay. So the timing for the G10 kicker is completely critical, right? If we're going to extract 1 bunch and only 1 bunch, the rise it has very narrow pulse width, right? You have to come on, kick the bunch, and go away before the next bunch comes around, which for gold is a quarter of a revolution period. It's very fast. So it has to be a very narrow pulse, and it's very easy not only spatially to miss the bunch, but in time, right? A relatively small change in the fine fine delay will change where you are relative to the bunch. Yeah.
Can you give us some examples, like what kind of instrumentation, like the you can
Sure. The BPMs, current transformers, principally those, right? You will see nothing at all. You will, right?
APR, BPM, orbit.
ATR BPMs, Rick first turn BPMs. They also have different integration windows, so they come on a certain time after FEV bunch, integrate the signal coming in, and then stop integrating, right? So we can move where that window is. And the windows aren't all the same width. I think the ATR BPMs have bigger windows than the ring BPMs typically. So you can get some and not get others and still have the same problem just because some of them are more tolerant of timing error. Typically, when we first start up, somebody will open up the windows as far as possible, right? And then we narrow them down as we tune up. Right? Because the longer you integrate, the more noise you integrate. So we'd like to see something, and then we'd like to integrate as little as possible around the button, so our tolerance becomes smaller and smaller. The flags, the damper, right? Anything that triggers on anything in the ATR, anything that has to trigger on the first turn, will be messed up by this, right? RF phasing,
Where?
right? The rev tick setup. So the rev tick, you set it up, and a rev tick is a labyrinth of a topic, right? But the RF expects the beam sometime after AGS extraction, right? The RIC RF expects the beam sometime after AGS extraction, just like the BPMs did, right? And so there's this trigger that we want to come out just as the bunch passes IR4, right? And so they time that in to coincide with that. So if we set up AGS extraction, then the RF group calls and says we had to move rev tick by a whole lot relative to where we used to use it, where we used to have it, right? It's not canonical anymore. We have to start. It's worth checking the timing down the line, right? So all of this is mostly to say that this fine delay does not affect just the G10 kicker, right? As it purports to. Everything about it seems to scream that it's just a kicker trigger. What could go wrong? But in fact, it's what determines when everybody downstream, all the instrumentation downstream, expects the bunch. Right? It moves fine delay, it moves the FEV bunch a little bit, and then the bunch relative to FEV bunch, the bunch relative to the trigger a little bit, and if we're out of tolerance, then we can really go haywire. Also, there are 3 of them, right? So this is a little bit strange. So the G10 controls actually only have one set point for the fine delay, right? There's only one slot where we can specify this trigger timing. Unfortunately, that timing is slightly different for blue and yellow, typically, and very different for green. It has mostly to do with cable delays, right? So green doesn't have to go all the way out to RIC RF, right? It just goes upstairs. The signal and the triggers only live pretty much in this building, right? Whereas the blue and yellow triggers have to talk to the RIC RF. So the cable delays are different, so the delay we need to kick the bunch is slightly different. So typically, tape and RIC injection manage which of these are being sent down to G10 at any given time. So when you request a blue bunch, RIC injection sends this value to the G10 kicker, right? And when you request a yellow bunch, it changes it to this value. When you switch to green bunches with tape, it sends this value. Which is important to note because if you go to the AGS extraction ring page, you'll see the value that's currently in the G10 kicker. And if you tune that one, it'll just get overwritten the next time you change the color that you're working with, right? So you would tune really with this, right? The final value, if you were to optimize G10, the final value you would want would have to go in here in order to be used for future extractions. Otherwise, it gets overwritten during the next toggle. Oh, and down here is the low intensity. This, like I said, this page is kind of one-stop shopping. It's very nice. Down here is the low intensity interlock. So we have a system that measures how much beam is in the AGS, the beam current in the AGS, as close to extraction as we can manage. And if it's below the threshold that you set here and the inhibit is enabled, then extractions will not happen, right? So this has bitten us before where we ask for it and the threshold is very low, and you can start putting things up on scopes, right? One thing that you'll notice though is that when you set up extraction on the scope, you're probably looking at the G10 kicker, for instance, and it won't trigger. And so one thing that stops it from triggering is HBMs only respond to green triggers, X and Y, and RIC responds to the appropriate colors, yellow or blue. Multiple extractions require multiple FEV requests. So this is an important point for gold. Sometimes we often will set up initially with one FEV extraction, right? Because the synchro process for 4 bunches is different. So RF finds it easy to set up for the first bunch, and then we work with 1 bunch extraction for a while. In order to go 4 bunches, it necessitates a timing change. We have to add more FEV requests. Okay, so just like for booster injection, we often have, we talk about the canonical scope setup, right? The tandem pulse, the booster injection transformer, that picture. There's sort of a canonical extraction scope setup. Sometimes we call this measurement of the bunch to kicker timing. So the things that we're looking at here, there are really only 2 pieces, there are only 2 traces here, and the other 2 are zooms, right? So this here is the AGS wall current monitor.
Can you write that in for us?
Sure. So this is the AGS wall current monitor, which is G5. And the blue trace here is the G10 kicker. And the lighter traces of each color, this guy and this guy, are zoomed. So this scope, which sits at MCR3, allows you to set a function right down here, which is just an inset, a zoom of a different, of another trace. So the light pink trace here is just expanded out here. This is nice because it can be tough to set yourself up on the peaks of any one of these bunches, but it's easy to see here. So the idea here is to, first of all, when we're first setting up, we would set it up such that the G10 kicker was actually kicking a bunch. And later on, if we're having stability problems, you want to see that the bunch's kicking timing is stable. So these guys are all circulating, right? And then after the G10 kick, there's a gap, right? So which bunch is it that is missing now? Like which bunch from over here is it that's missing? It has to be, so this is gold, and it has to be 4 back from this one, right? 1, 2, 3, 4. So he's here on this turn, then the G10 kicker fires, and then it's missing. What's important to note is that this interval here between the G10 kick over here and the bunch that you kick. So it's important to know which bunch it is that we're talking about when we're timing in, is non-zero, right? In machine, obviously it has to be 0, or pretty near, right? Kicker has to fire when the wall current monitor is at the G10 kicker. But the fact is that these timescales are very small, right? So there are cable delays that come from the wall current monitor, and there are cable delays that come from the G10 kicker. Both of these are hardwired signals. The G10 kicker actually comes in at MCR6, and is typically set up to be piped over to MCR3. So the interval that you measure on the scope is not necessarily 0. To set it up at 0 would almost certainly mean you would miss the bunch, right? So there's this canonical value of 1.6 microseconds, give or take a little bit. It's usually 1. The number I usually have in my head is 1.65, and that's the number that we usually set up on. And like I said, you could move this by this amount, right, and still kick a bunch, or move it backwards and still kick a bunch. But it would be, in some sense, the wrong bunch, right? It's not the bunch we're set up on. It would come too early or too late for the AGS extraction instrumentation to see. So that's one thing. For initial setup, we want to see that the bunch to kicker timing is what we typically would like to be. Another reason to set up this scope is if you're having shot-to-shot jitter, you want to make sure that this is stable from one extraction to the next. That can happen sometimes. If you have a lot of jitter, it's typically a synchro issue, and very often it will hop by 20 nanoseconds, so you get 2 modes, one over here and one 20 nanoseconds apart from that in either direction. And that typically means that you have this waste condition. So 20 nanoseconds is approximately a RIC RF bucket. So we're aiming at the wrong RIC RF bucket. And low-level RF can change the phasing of 2 triggers such that they're not hopping relative to one another anymore. But that's a pretty reasonable signature. A 20 nanosecond jump is a pretty reasonable signature that you have that race condition issue. So this is the same picture, slightly different. I apologize if the colors are flipped. That's a little bit annoying. So this is G10 now. This is the wall current monitor. And I do this in part, I'd like during the next run to get a series of pictures, one extraction after another, because during booster extraction I know that it's tough to talk about how the bunches are being extracted and then injected into the AGS, but it's easy to see if you have one picture after the other. So this is the next to last extraction, right? We have 4 bunches in the ring, we have 2 circulating, then 2 circulating, and then after the G10 kicker there's only 1. Right, so this is a similar picture in reverse to the booster injection picture, where we're seeing 2 bunches, 2 turns, and then on the next turn, there's only 1 bunch. Right, so unlike another difference to booster extraction is that booster extraction, we only ever extract all the bunches in 1 turn. Right? The kicker comes up, stays up for a full turn, and then goes away, and all the bunches come down BCA 1. In AGS to RIC transfer, as you probably know, we can take 1 bunch, right? You can take 2 bunches, you can take as many or as few as there are in the machine. So we typically tune up with 1, and then we can take full AGS cycles for gold, for instance, for protons. Okay, so that's the rundown of the in the ring part, right? After this point, we're out of the ring. Oh, I should note that this is the scope setup that you would use to diagnose the merge too. Right, we were talking about phasor bunches yesterday, and I didn't have a good picture, so what you would have here, so you have these typical bunch. It's of a certain height, and there's nothing in between them, right? If this was the first extraction, I would have 4 bunches of approximately equal height. If the merge went wrong, right, I would have spikes outside of the buckets, which were just the not well merged portion of the beam that remained in the old bucket. Right, so that gets us out of the AGS, and we can talk about APR if there are no questions about the AGS or not.
So if you have the rev tick signal available, and you put it on that scope, would it be like would bunch 1 always have the same delay from that signal? Like the first bunch extracted and then the second bunch extracted, they would always have like the same delay?
So rev tick comes out once every RIC revolution, so it would have the same relationship to bunch 1 all the time, and you'd be able to put them on one display, because the goal of the phasing of the rev tick is to put rev tick on the rising edge of bunch 1. Right, it has to be static, that's the point. So now the relationship between the first bunch and the second bunch is dictated by RIC RF, right? It's usually 3 buckets later. And so that would have to be fixed also.
It would be different than bunch 1, but still the same bunch 2. Bunch 2 would still always have the same delay.
Yeah, right. That's the goal of rev tick, right? Which is a RIC concept, but it's to tell the instrumentation where bunch 1 is, right? Just like for AGS extraction, everybody looks for the bunch a certain delay after FEG bunch. Once you're in RIC, everybody looks for the beam on a turn-by-turn basis, some delay after rev tick, right? And so bunch 1 always comes a certain number of microseconds, I suppose, after rev tick. The second bunch would come a certain larger number of bunches and so on. But those are right, the relationship is completely fixed. Right? Certainly the relationship between the bunches is totally fixed by the RF.
So if we had some timing problem, like with signal fix, like say the G10 bind delay is off by a quarter of a turn or a full turn, a quarter of a turn. Would that help?
Would that help? As in, would you see a problem there also? You would see, right, you would see changes all down the line. You would see a change in the extraction kicker timing, so you put that up on a scope and you would see that that's not, where it used to be. The injection kicker timing, right, we did this a few times where, in RIC injection, because it's in your face, you see that the injection kicker timing is wrong, and then we correct that. But that's usually symptomatic, right, of some underlying timing shift. It's not that the injection kicker has suddenly shifted, it's that something upstream has shifted, and now we have to change everything else, right? So that should set off red flag. And right, if you send somebody from RF out to 4 o'clock and they put the rev tick and the bunch up on a scope, you would see that that's different also. If AGS extraction timing is shifted. Right, because now the bunch comes out at a different time relative to when the rev tick is being generated. So all this stuff moves at once. Make sense?
Yeah. So
the relationship will be fixed but wrong. Go ahead.
No, didn't you just say that the
it would shift to a different relative time, and then we'd be stuck in that mode. Yeah. The AGS rev tick relative to a bunch has to be fixed cycle to cycle, right? That's the reason for being of the rev tick. Whether it's the same bunch is a little bit weird, right? Because for protons, there's only one.
So does Rick just take a bunch and call that bunch one, but it's not always bunch one in the AGS?
Okay, so for protons, again, right, we have to keep track, it's H equals 12, and there's only one bunch, right? And so we do, in fact, keep track, this AGS locked RF, right? We keep track of where that bunch is, right? When we inject from the booster, this trigger comes out that marks that bucket as bunch one, or bucket one, right? And we have to keep track of that one, because otherwise the chances of extracting properly at flat top would be 1 in 12, which would be pretty good. For gold, it's a little bit funny because of the merge, right? The harmonic number is grossly different.
Doesn't the rev tick get like set up
After the merge, right? So the question as to whether it has a fixed relationship, the answer would have to be yes after the merge, right? I don't know how we keep track of things through the merge. That seems insane to me. Somehow works, right? But right, so rev tick is sort of a meaningless concept before the merge, or not a useful one because you're going to change what you even mean by bucket one afterwards, right? But yeah, we have to know where the bunches are, right? The AGS knows where the bunches are. Otherwise, even for gold, the odds would be 1 in 3 for extracting, right? You can't just pick on a random bucket. I don't know if that helps at all.
Yeah, but so if you had this P10 fine delay problem, you would see it by looking at that signal at the same, like on that setup, the P10 trigger bunch disappears.
I see. You want to use you want to use the rev tick to distinguish one bunch from another?
Yeah, because you'd still be
Right.
extracting effectively, but you'd be, 4 or 3 buckets off.
Right, that's a fair point. So, yeah. Well, I don't know how that would work, but you're right. Well, you wouldn't be, if you were off by a turn, you wouldn't be able to tell, right? Because there's another rev tick, right? But you'd be able to distinguish parts of the turn, I guess.
I don't know if the brick extraction picks the bunch,
The same bunch
the
every
same
time.
bunch every time. So you might see the rev tick just show up on one of those 4 bunches of the trailer anyway.
That would be useful.
Right, that's my
The
problem with
The
gold.
rev tick has no use in the AGS RF system, right? It's a diagnostic tool for other systems. So the RIG RF doesn't care where the rev tick is when it extracts the I don't know. I never looked at it, so I don't
Right, it doesn't care, but it puts it there, so, right. The question is, I don't know. The answer is, I don't know. It's a good question.
To look at, something like that.
The trigger could FXM for transfer marker.
Right.
So we know when the first bunch extracted to AGS every cycle. I mean, maybe the system will add some delay to that, and then know when the first bunch comes to AGS, and then maybe some combination delay for extracting to it.
Right, that's the trigger I was talking about that marks bucket one. But whether the extraction equipment cares which of for protons before you're extracting is the question, right? Does it distinguish between bunch 1, 2, 3, and 4, or does it say just give me the next guy that rotates around? Right? I don't know.
Yeah, and there's more to that point, so I don't know how.
Right, I still don't understand how we keep track of things doing that. Right. That seems what bucket 1 is before and after seems to me to be meaningless, which is why we typically don't set up the rev tick before it with any degree of accuracy, because it's sort of meaningless.
Okay, can you remind me about AGS rev tick, the definition of that?
So it's the same, it's a similar concept to the rev tick, right? It comes out once a turn, and you'd like it to have a fixed relationship relative to some bunch. So that, for instance, the 2 meter pickup can look turn by turn and get a tune measurement, right?
So this is after merge or before?
Typically, we only set it up after the merge, right? Because it would be difficult at best to keep track of where you are throughout the merge, right? So we usually don't bother. And gold injection tunes, right? We don't have to know them very accurately because we're far from any resonances, right? The point is just to get surviving beam and things like that. We're much more concerned about two measurements for polarized protons, where it happens to be easier to set up the reptic also.
Before merge, we have FXM, and then after merge, we have at the rapid.
Yeah, right. Okay. Any other AGS questions? AGS proper. Right. Once you're through the H10 septum, now it's just a matter of transporting beam down the ATR to Rick injection. So the control for that is all in one. The controls for all of those magnets are all in one place. This AGS extraction transport, you select your line and power. And we have a whole slew of instrumentation in the ATR, flags, loss monitors, current transformers, and BPMs that we can use to measure and improve transport down the line, and to verify that the optics and the steering are correct. So I should note that at this point, gold is still 77, right? We stripped from 32 to 77 to BPA. There are still 2 electrons left, and this is the last stripping stage in the chain. So just upstream of UQ6, which is a few feet really past the stub tunnel, right? And I have a map to show you. You go through UGE1, and the stripping foil is pretty much right there. The titanium foil, that unlike the BTA foil wheel, it's just a plunger, right? It's either in or out. I think there's some impetus for making steps so that if we wear a point in the foil, then we can just step it by 1 beam size. But at the moment, it's either in or out. And gold, like I said, is stripped. The last 2 electrons are stripped, and now we have bare gold. You can't collide. It's kind of this funny thing. We circulated 77 at injection before. You can't collide it because the collisions actually strip the cross section for stripping the last 2 electrons. It's pretty large, so you collide, and then the electron goes away, and then you don't make it out of the IR because you go through the DS magnet and slap against the wall. Right? Your rigidity change. You get stripped while you're colliding, and so your rigidity changes, and then you won't circulate anymore. And the foil is out for protons because those are generally fully stripped. Right, so we'll just go through a little bit of geography of the ATR. I think most of you are pretty familiar with this. So some of the elements that we think of as U-line elements that are labeled U, so on, are actually in the AGS tunnel, which is important to know. If you have a problem with them and you have the lotto. So this is the AGS ring here, right? It's going this way. The H10 septum is somewhere over here. We extract and we come down the line. So here's the first current transformer. This has a similar status to multiwire 006. There's not a lot between the extraction equipment and this current transformer. So this current transformer can distinguish quite a few problems, right? If you're not getting beam here, then you likely have a problem in the AGS or with extraction proper. This is also what causes the whoop, right? The noise for extraction is determined, like the pitch is determined by the intensity here. So the funny extraction, right? That all comes from UXF1, which is important to note that if the whoop doesn't tell you a lot, right? It tells you you got here, and we have a long way to go before RIP. I think the whoop tends to inspire a sense of entitlement, right? That if there's a whoop, I should have beam at Rick injection, and if I don't have beam at Rick injection, I have a Rick injection problem. But there's a long way between the whoop and the promised land. So it's important to know, just to have in your head that the whoop and beam at UXF1 means something, and it does in fact eliminate quite a few problems, but it doesn't eliminate them all, right? So then we go through a series of elements, right? There are steering dipoles. The green guys are all BPMs. This is what we call the 4-degree bend, UARC4. Most of the time when you talk to CAST, they will talk about it as UD1 and 2, right? It's 2 dipoles wired in series. Like I said, this is UGE1, right? This is the penetration, and then this is the stub tunnel. So this is the part that you have to sweep after every AGS access, or at least check that it is swept. We rarely go in there, but just to orient you. So the stripping foil, like I said, you come down that labyrinth, and it's just right here, right next to the second flag in the line, somewhere down here is UF1. Right, that's another thing. If you have beam at UXF1, you can see what it looks like. There's a flag immediately adjacent to it. So you can characterize what the beam looks like coming out of the AGS if you you're making it through there, but it's a big fat blob, then maybe you have problems in the AGS. It's relatively rare.
But looking at it, they're looking at the dynasty.
Good point. Yeah, nice. So why is that true? So UF1 and UF2 will murder the beam, right? You will get nowhere after if you plunge UF1 and UF2. Well, it'll murder some beams. And then after that, the flags are somewhat less harmful for gold, for instance. So why would that be? Let's assume that they are no different from the downstream flags, but UF1 and UF2 will completely demolish.
Before the stripping point.
Right, so they are the stripping foil. Right, they will take off the last two electrons.
So why would UF2 matter if it's right next to the stripping point?
It's upstream. Well, you're right. Okay, fine. Yeah. Well, it's also it's a lot thicker, but it's not a big difference. We used to use UF2 as the stripping foil. You're right. So that was a little bit confused. But UF1 would certainly you wouldn't get anywhere. You certainly won't get through UF2.
Still gonna murder the beam because once you stop using the stripping foil, there's a different material in there, which then has a much lower stripping thickness. There's still a lot of it being used by going through that stripping foil.
And it's much thicker, I think. So the effect on the beam. One of the reasons we stopped using the old UF2 foil is because you lose 5% of the beam just due to the material in the foil. Whereas now it's less than 1% in theory going through our stripping foil. Right, and so this here is the first, the beginning of the W line. Sorry, that's the beginning of the 8-degree bend. So there's another big bend, right? These are the magnets that you'll typically have. Small drifts in these magnets can cause huge orbit excursions down the line. So when you're looking at ATR orbit display, and I'll show a picture of that, when you're matching up where the orbit excursions begin to go insane, you're going to want to know if that's right after a big bend, you can start with small tweaks of those magnets rather than trying to steer out big errors in the big bends with relatively weak steering magnets. And each one of these purple dashes all the way down the line are loss monitors, which are really useful for determining where you're losing beam. Unlike the loss monitors, right, I said at AGS injection, you can't see anything. In some cases, the loss monitors are way more sensitive than the current transformers. So you'll see problems on the loss monitors before the current transformer can show you that you're losing significant amounts of beam. So we have a significant bend here. This is the start of the 20-degree bends, right? There's some ambiguity because WR, you'll often call CAS and say that arc 20 is down, and they will show up at the R line, and they will tell you that it looks just fine. So it's important, right, to realize that there's some ambiguity here. We have two 20-degree bends, one in the R line and one in the W line. Another important thing to note is that RIC and the AGS are not at the same elevation. So booster to AGS, booster and the AGS are, right? So booster AGS transport is entirely horizontal. AGS to RIC transport, on the other hand, is horizontal and vertical. So in the W line, there are two pitching magnets that are called WP1 and WP2. So WP1 is here, and WP2 is here. Good times. So this whole, right, and if you go into the W line, it's kind of interesting, right? The beam line gets, right, this is the point where the beam line passes your hips and then your ankles, and then it goes through the floor into the rest of the W line. That's not the floor coming up, that's the beam line going down. So this actually has implications for polarized protons. The spin transport through BTA is a non-issue because you have vertical bends. These represent kicks to the spin, and so these have to be set and properly in order for the spin transport to be reasonable. They're also fairly strong magnets. They're horizontal apertures, so to get a very strong vertical field, right? One thing you can do is to make the pole tips very close. So to get a vertical bending field, you need horizontal field lines. And so these magnets, if you go in there, right, the beam pipe is typically like 2 or 3 inches in radius, I think. And then if these magnets just get squashed, it's kind of ridiculous. I didn't know this until the beginning of the last run. Very small aperture. So if you have losses at the pitching magnets, even though they themselves are vertical magnets, it's typical that you'll have to do horizontal steering because the apertures there are so tight. Right, so each one of these big yellow rectangles is a 20-degree bend, and then right at the end here, the end of the W line, this is the switching magnet, right, and then we branch off into the X and Y line. I should note also that there are chipmunks. I'm not sure that these locations are still entirely correct, but there are chipmunks at the labyrinth. This one is certainly there. That will also tell you if your transport is not good, but that should be a pretty a lagging indicator. Hopefully you realize that you typically what happens is you get chipmunks when like their line is idled or something like that. When you have really significant losses like the whole beam. And so this is the X line, right? This is the end of the last picture. This is the switching magnet. We'll come down here and you can see that, and this is apparent when you're in the tunnel, that the X and Y oscillators covered, right? There's no space for anything. Every last inch is covered in magnet, which you might expect for 90 degrees worth of bending. Something also that's kind of interesting, there are almost no quadrupoles, right? There are a few, mostly at the end, for matching it to Rick, but there are almost no quadrupoles, and that's because these are all combined function magnets. The 8 and 20 are also combined function magnets, so there are no quads within them. So all the focusing happens purely, as it does similar to the AGS, based on the quadrupole moment of each magnet. Right, and then at the end here, and we'll talk about this more in the Rick portion, I think, is another vertical step. So we're still not on the same plane, even after the long decline in elevation in the W line. We're still not on the same plane as Rick. The last step in Rick injection is still vertical. So Lambertson is the septum at the end of the HR line, and that has two channels. Right, for the previous septum, right, they've all been in a plane, and extracted beam and circulating beam, all in one plane. But the Lambertson has this. The incoming channel is actually skewed horizontally and vertically relative to the circulating beam. And there's another pitching magnet at the end of each line, XP1 and YP1, that provide the last kick downward into the circulating beam path. Actually, you travel above the circulating beam until the injection kicker, which then puts you exactly on the circulating orbit, hopefully. So it's very quick. This wasn't meant to be, a primer on how to tune individual errors. That can get kind of complicated. One thing to note is that flat isn't always better, especially towards the end, because you have this dip vertically down into Rick. The last few BPMs in the ATR tend to have pretty strong downward spike, whereas typically. So as I said, the ATR is pretty well instrumented. It's easy to see a lot of things. It's easier to see things what's going on in the ATR typically than it is in the BTA. So we have ATR display. This is completely non-invasive. You can look at every orbit if you like. These are terrible orbits, vertically in particular. So you can monitor the orbits, and I would typically have this and the loss monitor display up if I were steering. The nice thing about ATR orbit display is this plot up here. You may be familiar with schematics like this. They appear starting now and in a lot of the RIC applications. They tell you what major magnets you're dealing with. So up here, the convention is that the tall, thin rectangles are quadrupoles, and the short, wider rectangles are major dipoles. This is the 4-degree bend, 8, 20. And the pitching magnets are here and here. And then the little circles tell you where, and squares rather, tell you where the BPMs of each plane are and where the smaller orbit correctors are. So you can match up distortions in the orbit with appropriate magnets to correct that error. And like I said, you can line this up with losses, which are often more sensitive to small problems than the current transformers will be. You start to see things on the current transformers. These actually saturate very quickly. So these are both non-destructive. The flags tend to be, even the ones that aren't effectively stripping, they tend to blow up the emittance of the beam. It's a little worse for gold than it is for protons. That's why, for instance, for protons, we can plunge 3 at a time and take emittance measurements because the effect is relatively small, whereas for gold, we were plunging 1 in as a representative, right? We can take an emittance measurement and say, that emittance corresponds to some profile on one flag, and we use 1 as the representative. And if there are changes in that, you can go back and measure more carefully with a set of flags. Oh, and I should mention, the flags have to be set up carefully. That's a class in and of itself. Chris Zimmer. The emittance and the measurements that you get of the widths in particular can be very sensitive to the filters that you're putting in and to saturation of flags and things like this. So the flags are in particular willing to lie to you pretty constantly if you're not careful. And the answer can also be pretty strongly intensity dependent for the same reason. So it's careful not to make it's important not to make strong tuning decisions based on the flags, but I'm not sure that that's really a problem. Okay. So we didn't talk too much about AGS to rig synchro. As I said, it's relatively straightforward. There are some things to watch out for. In the booster, remember, we're ramping, and there's this whole business with the synchro table, and getting the phase and frequency correct then can be difficult because you're really only at the right frequency for an instant, right? So you don't have time for feedback loops to ramp down errors nicely and things like that. So you have to do all those gymnastics. But in the case of AGS to rig synchro, we have this long flat top. We'd like it to happen as quickly as possible, but things aren't moving out from underneath you, we hope. So in order for synchro to engage, what we typically like is for the main magnet to be completely flat. There's some ripple at the end if you come onto the flat top, so we'd like that to go away so that the radius isn't moving out from underneath us. And for the extraction bumps to be completely on. As I said, they do affect the frequency by changing the path length, so for a fixed momentum, it takes longer to get around. So the frequency with the extraction bumps on tends to be lower. So we don't want, if they're ramping when synchro tries to engage, we have a problem similar to the one that we have in the booster where the frequency is moving out from underneath you. So you would like for the frequency and the radial average, the measured radius, to be stable before synchro engages. And you can measure both of those things, right? We have a signal called AGS RF sweep that you can put into the frequency analyzer, and you can see whether the frequency is flat or ramping. In addition, we have a scope signal called the radial average where we can measure the radius and see that it's flat when synchro engages, just before synchro engages, I should say. This signal here labeled AGS to rig synchro is the phase error. So you see that when the radius is changing, we're probably still ramping here. The phase error between the AGS RF and the RIC RF is changing quite rapidly, right? Because the buckets moving at a different frequency are moving relative to one another quite quickly. At some point, synchro kicks in and starts to correct this, right? The frequencies are such that the buckets don't move relative to one another, so that the phase motion slows down, and then the phase error is ramped down in a way similar to boosted AGS extraction. So this is all done with feedback loops, right? Rick provides an RF reference. We measure the difference between the two frequencies and the two phases. And in this case, we don't need synchro tables or anything. There's just feedback loops that diminish those errors. One thing to note, this comes up all the time with AGS extraction. There are 4 available parameters to determine the energy and the frequency of transfer, right? There's the B field, the frequency, the momentum, and the radius. I suppose we'll come back. Okay, you can pick any 2 of these, right? And then the other 2 are fixed, right? That's the general rule. So, and the RF wiki actually has the equations that relate all these together. But in our case, right, the B field is fixed. Right? The B field at which we're extracting determines the energy at which we're extracting. So we hold the B field static, and the frequency is what we want to be the same, right? The frequency is the target value. So in order to get the frequency and the B field to be the same, these guys have to move, right? We're specifying 2, and the other 2 are predetermined. So what happens during synchro is the radius will get wangled around, right? So you can see when synchro engages, prior to synchro, right, we talked about this. On the ramp, we're on the radial loop. So the frequency is determined by the radius, and it's measured by those 2 pickups. And then at synchro time, there's nothing keeping the radius 0, right? Nothing intrinsic keeping the radius 0. So the synchro system will pull you to whatever radius it needs to get the frequency right. Fix the B field, and the golden value is frequency. Phase is just an arbitrary, right? It has to be right, but it doesn't come into this calculation. So the point there is that what we would like is very often when you have problems with ATR synchro, one thing you can check right away is to see if the radius that we engage synchro at is the same as what we end up with after synchro is done. There's a significant difference between the 2. One thing that can happen is that when synchro engages, it needs to move too quickly, and you can actually, the RF can sort of lose its grip on the beam. So rather than move the radius, the buckets move, the beam doesn't, and so we're no longer bunching, and the beam debunches. And you can extract, again, right, you'll kick the beam, maybe, and you can't move the radius anymore. So if the radius is sufficiently large, is close enough to correct, you can still kick the beam out, and it may even look bunched, but there's not going to be much of it, because you will only kick out the portion of the debunched beam that fits on the D-type kicker. So that's one thing, and one way to diagnose that, right, the current transformer won't tell you that. It doesn't know the difference between the bunch and the debunch beam. So efficiency from that point of view will look exactly the same. Two things can tell you that you have beam that is debunched. One is the wall current monitor, right? You'll have DCCT, but no wall current monitor signal, because the wall current monitor can't see DC beam. And actually there's a blue trace on the lower right-hand side of the AGS current transformer that I don't think is used very much. It's called the peak detect signal. So that is a measure of how tall the bunches are. So if you have current transformer signal and that drops to 0 at synchro time, that's an indication that you've been debunching the beam, right? The most direct measurement of that though is to just put it up on the wall current monitor. So that's one thing, and another thing is that if you are in fact losing beam, it could be trying to take you to a radius that is simply not inside the aperture of the machine. Remember that the extraction bump, like we said, is 40 millimeters. It's meant to put you near the aperture of the machine. And so we have a certain tolerance for radius error. So if in order to get the phase correct, it has to move the radius by a great deal, then you can lose beam just because of this radial shift. And so the fix for that is, again, to try and match the radius before and after synchro is on. And so that all that can be done in AGS beam control by changing the radial steering. The function before synchro starts, right? Because after synchro starts, it doesn't care about radial steering anymore. Right? The radius is entirely determined by this need to get to the right frequency.
If debunking happens, what do we do? We adjust the radius before synchro loop turn on, or?
That's right. So you'll see that the radius before and after synchro are very different. And because it has to change so quickly, the beam doesn't stay bunched during the process. And so, right, changing the radial steering before synchro starts will typically help that.
From where?
AGS beam control.
I mean, what time?
So there's a synchro start trigger. It's a real time, so you can check the timing of that. I think. Oh, there. So an AGS extraction ring, there's a delay from T0 when synchro will start. Really? No.
2100. 2100 it starts, right?
That sounds right. So that can't be
That might be before.
300. Extraction's at 850.
You're on user 3 there, so whatever.
Oh, so okay, so maybe we're not set up at all. Okay, fine.
We're gonna lower it.
Yeah, right. So I think you're right. I think it's something like 2100. So I mean, there's a non-trivial amount of time between synchro start and AGS extraction. Right.
Just to correlate this is that's the point where there's a real drop in the RF voltage too. Yeah.
I think that's true, right? Because we don't need so much RF voltage at AGS extraction. We need the full voltage for acceleration and electron
when you get to the black dot.
There's the peak, which is at peak B dot, but then it drops a little bit, and then it drops way down to about half of whatever the nominal function is, at about 2100 volts.
Yeah, last time I remember when we have this synchro log, we even try to adjust the sectional pair, the sectional. Yeah, make it more stable, maybe the units the beam when the synchro loop turn on is too big.
Mm-hmm.
So okay.
But I do remember for the lower energy gold, right, the beam was not so stable at flat top. And so that was a transverse issue, largely unrelated to synchro, except in so much that the beam is bigger and so you have less tolerance. So the process for diagnosing ATR, transport down ATR is similar for BTA, except you have more to look at, which is nice. So the first thing I would look at is the orbit and the loss monitors, and look for orbit distortions, starting with really big kinks in the orbit near the bigger bends. One thing to watch out for is if anything is tripped recently, particularly the big bend, when you bring them on, similar to the BTA situation, they're history suspects. So you may not get the same field for the same current. So even coming back to the same current, you may have tuning to do. Right, so that's pretty much it. As I said, it's similar to boosted AGS extraction from the bird's eye view, right? There's synchro, bump, interceptum, and then transport down the line. And the method for diagnosing these things is pretty similar. Define what time you're talking about pretty strongly, right? Am I even making it to the T10 kick? Are things triggering properly? I'm not getting out. And then the transport line is relatively straightforward because you can see everywhere, right? You have this nice coverage of the loss monitor. So this has the troubleshooting list. I think we talked about most of these things. Some of them came from earlier talks, right? Very poor AGS extraction. you have consistently you get the same fraction of the beam, sometimes that can be a problem with the merge. Actually, there's this rather strange thing, I think related to what Dave was talking about earlier. The VTA phase is off enough. The AGS, the ATR synchro, having tried to keep track of the bunch of the bucket with beam in it, you can slip a whole bucket. And so AGS extraction will inject into the AGS into what is essentially the wrong bucket, right? So for protons, where we can keep easy track of it, you'll inject it to bucket 2, everything will look fine, except AGS extraction will then get messed up because we've selected the wrong bucket. We'll take on an empty bucket.
But this is what he's talking about? Like,
That's a
this is-
similar, I mean, it's a similar issue, right? How do we keep track of the bunch throughout the cycle? Which is why, incidentally,
Yeah.
we decided not to run the booster synchro that time.
Mm.
Right, that was the question.
So this was your question, right? When you mentioned that thing.
The red tip.
Yes.
Something
The
analogous
same,
to
right?
red tip, you're saying? This wasn't my question.
I'm saying you can mark the wrong bucket in the AGS as having beam in it by having BTA off by too much.
But this wouldn't matter with gold, right?
Is there beam in every bucket at AGS extraction?
I guess after the harmonic of 12, I guess there is not.
Right, there are only 4 bunches, H equals up, so you can still miss bunches. Like I said, it's a little more complicated because between AGS injection and extraction is the merge, and right, keeping track of bunches is murky in my head, so.
Well, if you're off BPA phase, you'll see maybe bunches too, water side.
That's true because
Yeah, because
the phasing of
through
the
the
merge
merge
cavities is relative to this, right. So this is similar, talking about, the other symptom of this merge going bad is that you have beam left over after 4 extractions, beam on UXF1, or really any of the current transformers down the line, right? You'd locate the point of the loss with the orbit system and the BLMs, being careful to make sure that you've ramped the ATR, which is important, right, because the set points can lie to you, right? The set points may all be fine, but the readbacks, right, you need to make sure that the set points and the readbacks match. And we talked a little bit about the jitter. Very often, you can fix that by centering yourself in G10. Either, right, putting yourself really in the mouth of G10 in the flat field region there, or, again, more of a problem during setup, right? If you're kicking on the edge of G10 rather than the peak, right? If you're on here, the jitter in time is not so bad, but if you're here, for instance, right, a small jitter in time gets you a huge difference in the amount of kick that you get. Okay? Any questions?
I have one question. Where is the threshold measured at physically? I forget where that is.
That uses the unnormalized current transformer signal. The time it's met in the cycle we measure it at, we have some control over, so you want to measure as late in the cycle as possible to be sure that you still have beam as late as possible. But there's a certain amount of time it takes to inhibit, right? So I don't know how close you can get to the actual CFD request before the inhibit won't get there in time.
You said the trigger is adjustable.
The time at which we measure and compare to the threshold is tunable. We typically don't, right? There's really no reason to. We put it as close as possible and then just leave it there. The threshold level certainly is up for grabs depending on what it is that you're doing, right? In some cases, our tolerance is, well, we don't want to miss a whole transfer, right? So you would set it at something that's better than 75% of the beam for gold. But in some cases, right, when we're filling for physics, you don't want to take even weak shots, so we set it very close to the maximum.
Okay. Thank you, Vincent. This was fantastic. I think we all got a lot out of that. Could you guys just stick around for a moment? Let me print out the sign-up sheet.